Section 2-7. Before we start this discussion about pH, let me review for just 1 second. Do you remember the 3 subatomic particles that atoms are made out of? The 3 subatomic particles that atoms are made out of. Protons, electrons, and neutrons, right? Okay. However, hydrogen is kind of a strange atom. It's very unique in the fact that hydrogen atoms are made up of a proton and a electron. Hydrogens don't actually have any neutrons. So when a hydrogen atom is split and it loses its electron, when it becomes a hydrogen ion, what we're actually talking about is a proton. Okay, and so when you see that H+, that is a symbol of a proton. And so when hydrogen loses its electron and becomes a hydrogen ion, that H+, that proton, that H+, is very reactive. And it can break important chemical bonds. And so the concentration of these hydrogen ions, or these H+, that are floating around in the body must be very narrowly maintained within a normal pH. And so the pH is a measure of the concentration of these hydrogen ions, and it's actually an inverse concentration, so it's 1 over the log of the concentration of hydrogen ions. And so the higher the concentration of hydrogen ions, the lower the pH. And so the pH scale runs from 0 to 14, 7 being neutral. So a solution with a very low pH from 1 to 7 is considered acidic. Okay? And acids have a lot of hydrogen ions, which is why their pH is low. 7 is neutral, and then solutions with a pH above 7, so 7 to 14, is considered alkaline or basic. They have a very low concentration of hydrogen ions in that solution. And so this is a really nice way to represent that pH scale, and it gives you some examples to help make this concept solidify in your mind. Okay, so if we could start at 7 being neutral, you have pure water, right? Now, slightly alkaline, you see blood. This range of blood right here. Slightly alkaline, but very, very close to neutral pH. To give you an example, we have saliva and milk as slightly acidic. Tomatoes, grapes, beer, vinegar, wine, pickles, those are acidic. They have a high concentration of hydrogen ions. Stomach acid is extremely acidic, hydrochloric acid. And you can see up here, just to remind you that as the pH goes down, as the pH gets smaller, you have an increase in the concentration of hydrogen ions. So it's an inverse scale. Okay? And as you decrease the concentration of hydrogen ions, the pH will increase. Okay? And so, for example, you have bleach and household ammonia and oven cleaner, which are some of the most alkaline or most basic solutions that we have contact with. And so I've been using this term acids and bases. Acids and bases and salts are in a group of inorganic compounds that dissociate in water to form ions. Okay? And so acids, by definition, dissociate into a cation that is always a hydrogen ion, and an anion, which is not hydroxyl, by definition. So the stronger the acid, the more dissociation occurs, the more free hydrogen ions that are present, and therefore the lower the pH. So a strong acid is hydrochloric acid, and as you can see, hydrochloric acid can dissociate into a hydrogen ion, which is the definition of an acid, and this chlorine salt. And bases then, on the other hand, will dissociate into a cation that's never a hydrogen ion. And some anion, that's usually hydroxyl, a hydroxyl group. And so the stronger the base, the more dissociation occurs, the less free hydrogen that will be present then, and the higher the pH, because what happens is you could think of that hydroxyl ion, that OH negative, that's kind of like a sponge for hydrogen ions. And so that hydroxyl ion that this base is dissociating to acts as a sponge to kind of soak up any free hydrogen ions. And so remember, pH is the measure of free hydrogen ions. So the less free hydrogen ions, the higher the pH and the more alkaline that substance is. The classic example of a base here is sodium hydroxide, which dissociates into a sodium ion, which is not a hydrogen ion, and a hydroxide, which will soak up any hydrogen ions that might be present in that solution. And so this is the classic example of a base then. And I said salts too. So salts then dissociate into a cation that's never a hydroxyl ion, and an anion that's never going to be a hydroxyl. So you're never releasing hydrogen ions, and you're not releasing hydroxyl ions. So it doesn't have an impact on the pH. Okay, so salt dissociates into a cation that's never a hydrogen ion, and an anion that's never a hydroxyl ion. Okay? And so it makes a solution. For example, think of the table salt, sodium chloride. And I had a picture of this example in a few slides earlier in the previous recording. In table salt, sodium chloride, in solution, it disintegrates into sodium ions and chlorine ions. Neither one of those are hydrogens, neither one of those are hydroxyls. And so it won't impact your pH as much as an acid or a base. And this dissociation of salts then makes a solution. And so examples of salts, which are important in anatomy and physiology, are electrolytes. Electrolytes are inorganic compounds whose ions conduct an electrical current in solution. And why is this important? Why are electrolytes, why are these salts important? What parts of your body might need to conduct an electrical current? What do you think? You can pause the recording and think about this for a moment. There are two main types of tissues that conduct electrical current, and those are muscle tissues and nervous tissues. Okay, and so these electrolytes, these salts, are very important, just as important as acids and bases. Now, in the body, maintaining blood pH in a homeostatic range of 7.35 to 7.45 is essential. And so we can stabilize the pH by taking hydrogen ions out of solution or by adding hydrogen ions into solution as needed. And so that's what buffers do. Buffers are compounds that can stabilize the pH by either soaking up hydrogen ions or releasing them, okay, depending on if you need the pH to go up or if you need the pH to go down. Okay, and so that ideal essential range for homeostasis is 7.35 to 7.45 for the blood. And so one of the important buffers in our bodies is carbon dioxide in the form of carbonic acid. You get carbonic acid by combining carbon dioxide with water, H2O, and you'll get carbonic acid, which is H2CO3, which can dissociate when needed and release those hydrogen ions into solution and then carbonate. And so we've reached another checkpoint here. I'm wondering, can you define pH and explain how the pH scale relates to acidity and alkalinity? And can you define the terms acid, base, and salt? See if you can do those from memory from what we just talked about. And if not, pause the recording and go back and review. The next section in your textbook looks at some of the important organic molecules in your body. And we're going to start our discussion of the major organic molecules with carbohydrates. So organic compounds, remember, with carbon and hydrogen, are essential to the structure of your body, and we have one very important group called carbohydrates. And this class of molecules all has carbon, hydrogen, and oxygen in a ratio of 1 to 2 to 1. So there's 1 carbon for every 2 hydrogens and 1 oxygen. And if you break up that word carbo and then hydrates, so carbo is in reference to the carbon, and then the hydrates is in reference to the hydrogens and the oxygens. And there's 2 hydrogens for every 1 oxygen. That, if you take a moment, process that, H2O, that's water, right? So carbohydrates are really carbon plus water, carbohydrates, and that's where they get their name. So this is the group that includes sugars and starches, which are used as in your body as a good source of energy. And we have 3 major types. We have monosaccharides, disaccharides, and polysaccharides. And so let's take a look at each one of those. Monosaccharides are simple sugars. They typically have 3 to 7 carbons. And you can take a look at that word and break it into little word parts. Mono means 1. So these are used as building blocks. These are the subunits for larger, more complex carbohydrates. Monosaccharides are typically polar, which means that they readily dissolve in water. And if you are wondering, how am I going to remember what dissolves in water and what doesn't dissolve in water? Like dissolves like. And if you can remember that water is polar, then any substance you come across that is polar will dissolve readily in water. Like dissolves like. Water is polar, so it dissolves polar things. So monosaccharides, which are typically polar, will dissolve readily in water. And you've probably seen this when you add sugar to your coffee or to your tea and then stirred it. It dissolves. It almost disappears, right? That's because that sugar is dissolving. It's polar. Glucose is probably the most important energy source in your body. It's the metabolic fuel that your cells will burn. Disaccharides then, the word part di means 2. So you have 2 monosaccharides joined together by a covalent bond. Those are called glycosidic bonds. And so you can form substances like sucrose and maltose or lactose, the disaccharides. And then when you have multiple monosaccharides and or disaccharides that are linked together by covalent bonds, you can generate these large molecules like starch or glycogen. Starch is typically what you'll find as storage molecule for plants. Glycogen is how animals store their polysaccharides. And so I'm going to stop the recording there, and we'll pick up with lipids, section 2-10, in the next recording.